On May 16, 1940, President Franklin Roosevelt stood before Congress, requesting 50,000 aircraft and an extensive expansion of ground forces. Yet behind closed doors at the War Department, a more urgent crisis loomed. General George Marshall had just received the latest inventory report, revealing the U.S. Army's devastatingly inadequate tank stockpile. Only 464 tanks, obsolete M2 light tanks with 25mm armor and 37mm guns. These were far from battle-ready. Just 2 weeks earlier, on May 10th, German armored divisions launched a blitzkrieg into France, a move that stunned the world. The French army, equipped with over 3,000 tanks, including the heavily armored Char B-1, was expected to hold. The Maginot Line, a marvel of fortifications, was believed to be impenetrable. But by June 14th, German tanks rolled through Paris. The campaign lasted only 6 weeks. American military attachés sent urgent cables back to Washington. The future of warfare was not about infantry or static defenses, but speed, armor, and coordinated mechanized assault. The German success was not just about numbers. Intelligence reports revealed that the Panzer III, with its 50mm gun and 30mm armor, and the Panzer IV, armed with a 75mm cannon capable of destroying fortifications, were already proven weapons. These were not prototypes. They had already conquered Poland in 27 days and were now dismantling the French army. America's M2 light tank, by contrast, was a relic, weighing just 10 tons, with armor vulnerable to anti-tank rifles. Sending American crews into battle in such machines would be a death sentence. General Adna Chaffee, head of the newly formed armored force, had warned about this scenario since 1938. Now, his warnings had become prophecy. On July 11, 1940, the Ordnance Department received orders to design and produce a medium tank capable of matching German armor, and do it fast. The Aberdeen Proving Ground in Maryland became the epicenter of America's crash program in tank development. Engineers worked around the clock, and design proposals that would normally take months to evaluate were being assessed in days. The challenge wasn't just designing a better tank, but building an entire industrial ecosystem capable of producing thousands of them. The clock was ticking. Everyone knew it was only a matter of time before America entered the war. The meeting at Aberdeen on August 29, 1940, established a guiding principle that would define American tank production throughout the war. Speed trumps perfection. Major General Charles Wesson, Chief of Ordnance, explained the doctrine simply. German engineers were pursuing the ideal tank: perfectly sloped armor, optimal gun placement, revolutionary suspension systems. This pursuit would take years. America didn't have years. The Ordnance Department needed a tank that was good enough to fight, simple enough to build, and fast enough to produce in numbers that could overwhelm any technical deficiencies. This was not ignorance or laziness, but calculated pragmatism, informed by how wars were won. The engineering teams pored over reports from Spain's Civil War, where Soviet T-26 tanks had seen combat, and analyzed the fall of Poland and France. One conclusion was clear: the side with more tanks, able to maintain and replace them quickly, would hold a decisive advantage. A perfect tank was useless if it took years to design and could only be produced in small numbers. 1,000 decent tanks could change the outcome of an entire campaign. Germany's approach was the antithesis of American doctrine. When Germany's weapons agency commissioned a new tank, it demanded technical excellence. The Panther tank, which wouldn't be operational until 1943, was developed after extensive testing of sloped armor, debates over engine specs, and competitive bidding. Every component had to meet exacting standards. The transmission alone underwent multiple redesigns. This was precision engineering at its finest, but glacially slow. America's engineers made a fundamentally different choice. Rather than build the perfect tank, they would build an adaptable one. Specifications finalized in late 1940 prioritized modularity. The gun mount needed to accommodate various weapons as they became available. The engine compartment had to be versatile enough for different power plants, depending on what suppliers could deliver. Armor would be adequate, but not exceptional, enough to stop most anti-tank weapons of 1940, but knowing it might be inadequate by 1943. The trade-off was clear: accept limitations now for the ability to iterate and improve quickly in the field. This philosophy echoed Henry Ford's assembly line. Ford didn't build the best car, but he built it faster, cheaper, and in greater numbers. In February 1941, Rock Island Arsenal in Illinois became the epicenter of American tank evolution. The Army had rushed the M3 Lee medium tank into production just months earlier, but by now its design flaws were glaring. The M3's 37mm gun, mounted in a fully rotating turret, was paired with a 75mm gun mounted in a sponson on the hull's right side. British crews testing the M3 in North Africa dubbed it a mobile coffin. The high profile made it an easy target, and the sponson-mounted gun had a limited 15-degree traverse, meaning the entire tank had to rotate to aim. Worse, its riveted construction turned the M3 into a deadly shrapnel machine when hit by armor-piercing rounds. The M3 was obsolete before it could be deployed in significant numbers. William Knudsen, former president of General Motors and now overseeing war production, wasted no time defending a failed design. On April 11, 1941, he assembled a team at the Aberdeen Proving Ground with an impossible mandate: fix everything wrong with the M3 in 90 days. Leading the charge was the Detroit Arsenal Tank Plant, a facility under construction even as it was tasked with designing and building the tank. This was American industrial improvisation at its most audacious. But the engineers weren't starting from scratch. They embraced what we now call rapid iteration, preserving what worked and cutting what didn't. The breakthrough came by sticking to modular design principles. Instead of creating an entirely new tank, the team retained the M3's proven lower hull and running gear, redesigning everything above the tracks. The sponson-mounted gun was eliminated. A larger turret designed to mount the 75mm gun with full 360-degree rotation replaced the old one. The tank's height was reduced by over a foot. Most importantly, riveted construction was replaced with welded armor plates, which not only strengthened the armor, but also eliminated the dangerous shrapnel problem when hit. Welding also sped up production. Each weld took minutes instead of hours. Vischer Body Division, which had been building Buick car bodies, mastered tank welding in just weeks. By July 1941, 90 days after the project kickoff, the first prototype rolled out of the Detroit Arsenal. It was designated the T6. The Army put it through rigorous tests at Aberdeen, driving it through mud, over obstacles, and firing thousands of rounds through its main gun. The suspension, borrowed from the M3 and refined, proved reliable. The Wright R975 radial engine provided adequate power. The cast turret, manufactured using techniques adapted from locomotive production, could be made quickly and consistently. On October 9, 1941, the T6 received its official designation as the medium tank M4. The British named it the Sherman, a name that stuck. The entire development cycle, from concept to approved design, took less than 9 months. By comparison, German tank development cycles average 30 to 36 months, sometimes longer. The Panther, for example, wouldn't be approved for production until May 1942 and wouldn't see combat until 1943, more than 2 years after its design began. By February 1942, the Sherman would already be rolling off American assembly lines in volume. In November 1941, the War Department made a decision that would prove even more significant than any design feature. Every Sherman tank, no matter where it was built, would use standardized parts. This was not just about convenience. It was about creating an industrial weapon system where the whole was greater than the sum of its parts. 11 major manufacturers received contracts to produce the Sherman: Chrysler, Ord, General Motors, American Locomotive Company, Baldwin Locomotive Works, Federal Machine and Welder, Fisher Body, Pacific Car and Foundry, Press Steel Car Company, Pullman Standard, and Lima Locomotive Works. Many of these factories had never built tanks, and most had never built military equipment at all. But each one was now tasked with producing Shermans that could swap parts with tanks built 1,000 miles away. This was revolutionary for military production in 1941. In Germany, tank production remained largely artisanal, with each factory building its tanks to its own specifications and tolerances. As a result, Panther tanks from different factories often had incompatible parts. Field mechanics found components that wouldn't fit together across factories. The American standardization extended beyond major components, including fasteners, electrical systems, and even toolkits. Every Sherman carried the same set of wrenches, all of which fit every bolt on the tank. Radio equipment mounted identically in every turret, and even periscopes, hatches, and seat assemblies were built to exacting specifications. This level of standardization allowed for zero defect production and was a key factor in the Sherman's success. The Army Ordnance Department implemented a master blueprint system where changes had to be centrally approved and distributed to all manufacturers simultaneously. When an improvement was made, say, a better final drive gear ratio, it became standard across all production lines within weeks. This created an invisible logistical advantage that grew stronger as the war continued. By June 1944, when the 2nd Armored Division landed in Normandy, their maintenance battalions carried parts that could fit any Sherman in the European theater. A tank damaged in Normandy could receive a replacement engine from one built in Illinois, a transmission from a tank made in California, and a turret traverse motor from one made in New Jersey. The repair time for a Sherman averaged 4 to 6 hours for major component replacements. By comparison, German repair cycles were much longer. A Panther with a thrown track might wait days for a replacement from the correct factory, assuming one could be found at all. The standardization also sped up training. Tank crews transferring between units found familiar controls, regardless of where their tank was built. Mechanics trained on one Sherman could maintain any Sherman. This wasn't the case for the Germans, who had a maintenance nightmare on their hands. A mechanic trained on a Panther couldn't necessarily repair a Tiger, and neither could easily work on a Panzer IV. The German arsenal was full of incompatible systems, whereas the American arsenal became a self-reinforcing ecosystem where every tank strengthened every other one through shared parts and knowledge. In January 1942, production lines at the Chrysler Detroit Arsenal tank plant began rolling, and the engineering decisions made months earlier began paying off. The Sherman's power plant was the Wright R975 Whirlwind, a 9-cylinder radial aircraft engine designed for training planes. Though an unusual choice, it was perfect for one reason: it was already in mass production. Continental Aircraft Engine Company was manufacturing thousands of R975 engines each month. No retooling or development delays were needed. These engines were reliable, already available, and could be diverted immediately to tank production. The R975 delivered 400 horsepower, enough to propel the Sherman's 30 tons to a top speed of 25 mph. While this was less than impressive compared to the German Maybach HL230 engine, which produced 700 horsepower, it was simple. The R975 had fewer moving parts than liquid-cooled engines. Air cooling meant no radiators to puncture, no coolant to leak, and no water pumps to fail. Maintenance crews could swap an entire engine in under 4 hours, using only standard tools and a crane. This was not the case with the Maybach engine, which required specialized tools, precise timing adjustments, and mechanics trained specifically on its quirks. German tank units in North Africa lost more tanks to mechanical breakdowns than to Allied fire. The Sherman's hull construction added to the time savings. Its welded armor plates, not riveted, provided a significant advantage. Riveting required drilling precise holes, heating rivets, inserting them, and hammering them while hot. Each rivet point was a potential weak spot, and skilled riveters could place only 40 rivets per hour. A single Sherman hull required thousands of rivets. Welding, however, allowed for continuous seams and could be done much faster. Fisher Body Division, which had been building Buick car bodies, mastered tank welding in weeks. A welded hull section that would have taken 30 hours to rivet could be welded in under 8 hours. By mid-1942, the entire assembly process at Detroit Arsenal took just 10 hours per tank, from the moment the hull plates entered the production line to the moment a finished Sherman rolled out the door. Ford's Willow Run plant, which built B-24 bombers, needed 18 hours per aircraft. The Sherman's assembly line borrowed directly from automotive manufacturing. Sub-assemblies were built on feeder lines, and final assembly took place on a moving track. Each station performed specific tasks with specialized jigs and tools. Workers didn't need to be master craftsmen. They needed to be trained at their specific station, and the tooling did the rest. The Germans, on the other hand, faced much slower production. A Panther tank required about 55,000 man-hours to produce in 1943, and even after streamlining, this number dropped only to around 35,000 by late 1944. The Sherman, however, required only 10,000 man-hours from start to finish. The math was simple. While the Germans built one Panther, the Americans could build 3 to 5 Shermans. The R975 engine and welded construction weren't the best engineering solutions, but they were the fastest. And in industrial warfare, speed wins. In September 1941, while American engineers were finalizing the Sherman design, Germany's Hermann Göring received alarming reports from the Eastern Front. Soviet T-34 tanks were decimating German panzer divisions near Smolensk. The T-34's sloped armor was deflecting German 50mm rounds at combat ranges, and its 76mm gun was shredding German Panzer IIIs and IVs. Hitler personally ordered the development of a medium tank capable of countering the T-34. The competition for the contract was fierce, with two major firms, Daimler-Benz and Maschinenfabrik Augsburg-Nürnberg, competing to design the tank. The development of the German Panther tank began immediately after Hitler's order. The competition between Daimler-Benz and Main quickly became a masterclass in how perfectionism can hinder speed. Daimler-Benz submitted a design that closely mirrored the T-34 diesel engine, featuring heavily sloped armor and rear turret placement. It was practical, buildable, and could enter production quickly. Mann's design was far more complex, incorporating a front-mounted turret, a gasoline engine, and armor sloped at 55 degrees from the vertical for maximum deflection. The two designs were so different, they might as well have been for different tanks. The Waffen-SS, the tank development branch, spent months evaluating both proposals. Engineering committees debated over gun mantlet designs, and specialists argued over plate thickness and slope angles for the armor. Hitler himself weighed in on turret size. The deliberations stretched from late 1941 into early 1942. In May 1942, Mayenn's design won approval, but that didn't mean production was immediately underway. The Panther required specialized tooling that German factories didn't have. Sloped armor plates couldn't be stamped. They had to be rolled and welded at precise angles. The interleaved road wheel suspension, which offered superior cross-country performance, required machining tolerances that slowed production to a crawl. Each road wheel had to be individually fitted. The Maybach HL230 engine, capable of 700 horsepower, was a marvel of engineering but a nightmare to manufacture. Its complexity led to constant supply chain bottlenecks, with cylinder blocks cracking during casting and crankshafts failing quality control. Delivery schedules slipped month after month. Finally, in January 1943, 16 months after Hitler's initial order, the first Panther rolled off the production line. It was an impressive machine, armed with a 75mm KWK-42 gun with exceptional penetration and sloped armor nearly impervious to most Allied anti-tank weapons. Despite weighing 45 tons, it had good mobility. However, it was plagued with issues. The transmission, which wasn't designed for the tank's weight, failed constantly. Engine fires broke out due to fuel system leaks. Of the 250 Panthers rushed to the Battle of Kursk in July 1943, nearly 200 broke down before seeing combat, with many catching fire during the approach march. German tank recovery units worked around the clock, trying to salvage the disabled Panthers while under Soviet artillery fire. Even after initial bugs were ironed out, Panther production never reached efficient scale. Mann's Nuremberg plant managed a peak production of 250 Panthers per month in 1944. Daimler-Benz's Berlin Marienfelder plant added another 100 per month, with other manufacturers contributing smaller numbers. Total monthly production across all German factories peaked at around 380 Panthers. By comparison, American factories produced 2,220 Shermans in July 1943 alone. The German pursuit of technical excellence created a weapon system that was undeniably superior in one-on-one combat, but was never produced in sufficient quantities to affect strategic outcomes. The Panther's 3-year development and production cycle, from September 1941 to the first combat-ready tanks in mid-1943, meant that it arrived too late and in too few numbers. By June 6, 1944, as Allied forces stormed the beaches of Normandy, the mathematical reality of tank production became evident on the battlefield. The numbers told a story that no amount of superior engineering could overcome. By D-Day, American factories had produced 49,034 Sherman tanks, while German factories had built around 6,000 Panthers. This created an 8.1 ratio before a single shot was fired. But the real disparity appeared when availability rates were factored in. The percentage of tanks actually combat-ready at any given moment. The Sherman's availability rate in Normandy was around 85%. Out of every 100 Shermans shipped to Europe, 85 were operational at any given time, with the other 15 undergoing routine maintenance, awaiting parts, or being repaired. This was exceptional for armored vehicles in combat conditions. The Panther's availability rate was much lower, hovering around 35 to 40% in the summer of 1944. Out of every 100 Panthers, only 35 to 40 were capable of fighting at any given time. The rest were sidelined with mechanical failures, awaiting specialized parts that might never arrive, or being cannibalized for components to keep other tanks running. Let's break down the battlefield math. The 2nd Armored Division landed in Normandy with 186 Shermans. Even after combat losses and maintenance issues, they could count on 150 to 160 tanks being ready for action on any given day. The German Panzer Division, considered an elite formation, had about 100 Panthers in Normandy. On a good day, maybe 40 of them would be operational. The American division could absorb losses and continue fighting. They had replacement tanks arriving weekly from supply depots. When a Sherman threw a track, mechanics could replace it in hours with parts that fit any other Sherman in the theater. When a Sherman's transmission failed, a new one arrived on the next supply truck. The Panther crews faced a different reality. A thrown track could sideline their tank for days. The interleaved road wheels required removing multiple wheels to access the damaged track. A transmission failure often led to catastrophic results because replacement transmissions were not available in the supply chain. Panthers were often blown up by their own crews rather than abandoned because recovery was nearly impossible. German recovery vehicles couldn't tow a 45-ton Panther across country, and Allied fighter bombers made road recovery suicidal. Despite its technical superiority in certain areas, the Panther's production limitations and reliability issues meant that it was outclassed by the sheer numbers and logistical advantages of the Sherman. The Panther's fearsome reputation in tank-on-tank. Combat becomes irrelevant if it can't reach the battlefield. Allied commanders in 1944 fully understood the importance of numbers. American tank doctrine didn't call for Shermans to engage Panthers head-on. Why would they? A Sherman crew that spots a Panther simply calls in artillery, air support, or bypasses it. The strategic goal isn't to destroy every German tank, it's to advance. Shermans can afford to avoid unfavorable engagements because there's always another Sherman, another route, and another axis of attack. German commanders, however, can't afford to avoid any battle because every Panther lost is irreplaceable. When the Panzer Lehr division loses 40 Panthers during the Normandy campaign, those tanks are gone for good. No replacements arrive. The unit is rendered combat ineffective. Meanwhile, when the 2nd Armored Division loses 100 Shermans, replacement tanks and crews arrive within weeks, and the division keeps fighting. The brutal truth of tank warfare lies in availability and replaceability, not armor thickness or gun penetration. Superior engineering means little if the superior tank is broken in a depot, while the inferior tank keeps advancing down the road. By August 1944, the Sherman had proven something the Panther never could: adaptability under fire. Since production began in early 1942, American engineers had created over 50 distinct Sherman variants without halting assembly lines. The M4A1 used a cast hull, while the M4A2 featured a welded hull with different engines for various theaters of operation. The M4A3 incorporated a Ford GAA V8 engine, and when radial engines became scarce, the M4A4 was developed to accommodate a Chrysler multi-bank engine, 5 automobile engines connected to a single transmission. Each variant shared the same basic chassis, turret ring diameter, and track width. Crews could transfer between variants with minimal retraining, and maintenance crews found familiar systems with minor variations. The modularity extended beyond hull and engine swaps. In January 1944, reports from Italy showed Shermans needed better armor to withstand German 75-meter to 80-meter guns. Within weeks, field modification kits arrived. Applique armor plates that could bolt directly onto existing glacis plates and turret fronts. Crews installed them in hours without requiring a factory recall or production line shutdown. In March 1944, the British requested a Sherman variant equipped with their 17-pounder anti-tank gun, capable of penetrating Panther armor at combat ranges. The Sherman Firefly entered production within months. The turret ring, standardized from the beginning, allowed for manageable modifications to accommodate the larger gun. By June 1944, every British tank troop in Normandy had at least one Firefly mixed with standard Shermans. The Sherman also spawned specialized variants that German tanks couldn't match. The M4 dozer mounted a bulldozer blade for clearing obstacles and filling craters under fire. The M32 tank recovery vehicle used a Sherman chassis with a crane and winch, capable of recovering disabled tanks in combat zones. The duplex drive Sherman, equipped with a collapsible flotation screen and propellers, could swim ashore during amphibious assaults. 33 of these made it onto Normandy's beaches under their own power on D-Day. The Crocodile variant mounted flamethrowers, and the Crab featured a mine flail system. Each variant leveraged the proven Sherman platform, ensuring reliability and interchangeable parts. In contrast, the Panther's technical sophistication made field modifications nearly impossible. The interleaved suspension couldn't be easily altered, and the entire system was engineered as a package. The transmission was already overstressed, and mounting different weapons or equipment risked catastrophic failures. German engineers designed specialized vehicles from scratch rather than adapting existing platforms. The Jagd Panther tank destroyer shared the Panther chassis, but it required entirely different production tooling. The Berg Panther recovery vehicle took 18 months to develop and enter service in limited numbers. Each specialized German vehicle became a logistical nightmare with unique parts requirements. The Sherman's greatest legacy lies not in its combat record, but in the industrial philosophy it embodied. Fast iteration trumps slow perfection when production timelines are critical. Standardization enables scale in ways bespoke engineering never can. Good enough, produced in volume, defeats excellent but scarce. The Germans built magnificent tanks that arrived too late and broke too often. Meanwhile, America built adequate tanks that were available everywhere and kept running. By the end of the war, in May 1945, American factories had produced nearly 50,000 Shermans across all variants. Germany had produced roughly 6,000 Panthers and 2,300 Tigers combined. The numbers had already decided the war long before the final shot was fired. The engineers who designed the Sherman in just 9 months, using parts already in production and prioritizing speed over perfection, understood something the German engineers never grasped. In industrial war, the factory is the ultimate weapon.